Good morning, students. Again, we're enjoying the nice spring weather, and I hope you are too. It's always nice, like I said before, to enjoy a little less rain. We always need rain, but I'm grateful for this. And of course, maybe we'll get a little rain when the pollen count gets a little bit high, but I'm very happy about the nice temperate weather. What we want to do today is to cover Taylor polynomials and Taylor's theorem. And I just want to make one comment. Um, when I was assessing your test, I noticed in general that there were some good things. However, there are gaps in your reasoning at times. The thing that I'm looking for is just a general logical flow. And so as you think about your test, go back to the solutions and look at what I've written out, because it's just like what I do in lecture. And I think a lot of you are improving. I think sometimes anxiety can get the best of you and you get nervous. But again, that's the part of growing your mathematical background. And so just be sure that you are using your own notes. Again, the resources that I offer in Blackboard are certainly accessible to you for a test, but anything else would not be. So there has been an improvement on that end, and I appreciate that. Um, a lot of students have noticed that the Calculus 2 is critical to your understanding of analysis, as is Calculus 1. And then when you get to Calculus 3, you just see how it fits together to look at functions of 2 and 3 variables in curve theory in the plane and in space. So the nice part about Cal 3 is that you get to use all of the structure that you have learned in the previous 2 courses to really make a very, very nice course. So again, just remember that what we're doing now is building a foundation. And though sometimes it may get a little bit on the tedious side, it's certainly a worthwhile pursuit. So now what I want to do is cover Taylor's theorem and the Taylor polynomial. I think you'll like this discussion. It's very, very calculus-like. And when I say calculus, we do some differentiation, we do some arithmetic, we just do all the things that you would normally think of in a math class. So this will be the Taylor polynomial. And I'm also going to give the term Maclaurin polynomial in a few minutes. Taylor polynomial and Taylor's theorem. Now, when we refer to a theorem, or in this particular case, let me, gosh, I just lost my, always hit the mouse and then everything goes haywire for me. There we go. Make a little more space on my desk. I've got a desk. This is very nostalgic for me. The desk that I use has actually been in my family for so many years. I don't want to date myself, but it has nostalgic value. As you go through life, you hold on to certain things, and then there are things that you eventually have to relinquish because you can only have so much stuff. But this is this is one thing that I've kept all these years. So when we think about a polynomial, at least in terms of calculus, we want a polynomial that showcases calculus. So what we're going to do is suppose f is, and what I'm going to use as a notation, we're going to say Cn. This is going to mean continuous derivatives through order n. And then we're going to actually add another hypothesis when we state Taylor's theorem. So maybe we have an interval a to b, or maybe we just have the interval I. And sometimes we'll write it this way. So this will mean continuous derivatives through order n on the interval AB or the interval I. That's just the notation. And what we want to do, we're going to say where C is fixed such that either we have C between A and B or C in the interior of I. And when I mean interior of I mean I don't want an endpoint. So when we talk about the interior of an interval, we're staying away from the endpoint. So we're inside, so to speak. So we can approach the C from either side in that interval. And what we want to do is define a polynomial. Now we're going to see why it's actually a good polynomial, but for right now we just need to use it and commit it to memory. And the usual notation will be P sub n for order n of f. Now, like I said before, this C is going to be kind of what we call the center point or the point of expansion. And we're going to write f of C as our constant term, and then we're going to move through order n. The next term will be f prime of C times x minus C. So we're basically taking a function and having it agree at these n plus 1 values. That is, we're going to have f of C, f prime of C, f double prime of C, all the way up to the nth derivative. And then, of course, this is going to start reminding you of differentiating polynomials where you get factorials. So we're going to have f prime double prime of C divided by 2 factorial, x minus C squared. So what's nice about Taylor's theorem is it's eventually going to be an infinite series, a series of these objects. And that's basically why we have to start with the polynomial and then branch out to that. Then we have the third order polynomial, 3 factorial, x minus C cubed, and we just keep going. And we'll do some examples where we do like second order and third order to give you some practice. And then we end with the nth order derivative. Again, you see how the order of the derivative and the factorial coincide. So we get n factorial x minus C to the nth power. This is called the Taylor polynomial. Taylor polynomial. And again, why is it that we are interested in this particular construction? You're thinking, well, Professor Ron, it looks like you just made up a calculus polynomial, and maybe it does. But I assure you, I didn't just say, okay, here's something, we're going to look at it and never speak of it again. We've already been working with this in the shadows, so to speak. We just never referred to it. And when we start looking at some of the computations, you're going to see that it's always been in the background. So the idea, like I said before, this notation, continuous derivatives. That is, ladies and gentlemen, when we look at the derivatives, they're continuous on I. Continuous derivatives on I through order n. Sometimes, ladies and gentlemen, we need C infinity. We need all orders of derivatives to be defined and continuous. And that we have functions that have that property. We have functions that are very well behaved. So what we're thinking of in this case is that when we consider the Taylor polynomial, we're talking about functions that we're probably used to working with right now. And we're going to look at different representations of them and then figure out a little bit down the road that it turns out to be something very beneficial to us, and then pretty much tells us how our calculator works. So with all of this, how does this fit into a nice calculus theorem? Well, that's Taylor's theorem, and I'm going to state that. Now, I've got a nice write-up of the proof of this in the Blackboard notes. And like I said before, I didn't plan to go through that. I want to spend a little bit more time on the computation. The only thing is that the proof, though it's a very elegant application of Rawls' theorem, it's not as instrumental in helping you use the theorem. So what I want to do is have you look at that and basically understand how we evolve a telescoping sum. We love telescoping sums that basically produce the result that we're going to use. So it's a very nice proof. But again, if I have time to say more about it, I will. But for now, I want you to look at the proof that's written up in your Blackboard notes. So now let's go ahead and write this down. Suppose we're going to have a similar hypothesis here. F is Cn on I, continuous derivatives through order n, on the interval I. This is kind of what I put this in parentheses because it's a little bit redundant, on the interval I, containing C. And remember, again, like I say, C is in the interior. It's not an endpoint. INT is short for interior. And that we need that n plus first derivative to exist. And the n plus first derivative exists on I. We don't necessarily need continuity, but we definitely need that it exists. Maybe it might have trouble at the endpoints, or maybe it's fine. But the proof doesn't require any more than this. We just need the existence. For any, and the Rawls theorem is what gives us the Z in this theorem. You know, the Rawls theorem is where you find a point between A and B so that the tangent line is horizontal with the hypotheses of differentiability and continuity of the function. So this is a major use of that. So for any x in I, you can fix an x, and any x you take, there exists a z. And we're going to say, ladies and gentlemen, between x and c. So we don't know basically where x is. So for instance, if we've got this interval here and maybe we've got c, maybe x is right here, okay? Or maybe x is on the other side of c, we don't know. So the z is going to be in between. So that's about the best we can say. So z will be in between c and x. So between c and x. And such that, and this is where the beauty of the theorem falls out. Taylor's theorem is a major result, like the chain rule, like the mean value theorem. We can express f of x as the sum of the Taylor polynomial that we just wrote up here, plus a remainder term. Of course, we always have to pay for the approximation. So basically, we get a new construction for f. And then, just like we've seen before, the remainder will basically allow us to estimate error involved. Say if we approximate a function with a polynomial, how good is it? Is it good enough to solve the physics problem? Is it good enough to solve the math problem? With this many terms, is it good enough to solve the engineering problem? So where, in this particular case, Rn of f, this is called the remainder term. It looks like this. This is where we take the n plus first derivative, evaluate it at the z between c and x. So sometimes we know z exists, but we can't really get our hands on it. So what we have to do is make an estimate on the upper bound of the n plus first derivative. So that'll be a technique I'll show you that how to do, and it's doable. And then of course, we have n plus 1 factorial, just extending the idea of factorial here. And then of course, x minus c to the n plus 1. So again, these look the same pretty much. The only difference is now, instead of having the c here, we have the z between c and x. So this is basically the equalizer, so to speak. If we just chop it off here, what makes the inequality? Well, the remainder term. So it just takes up the slack, so to speak. So the remainder term is essential. And of course, when we look at the infinite series, we will have to analyze it even further. And I think you can tell that it would certainly have to converge to 0 if this were ever going to work. All this stuff that we've already talked about with the real series and all, it will have a great impact on this. But notice now the big difference here. Before, we were just dealing with series of real numbers. Okay, so now we're introducing the concept of a Taylor polynomial that has calculus in it, but it's got a variable. Okay, so that's going to be how we extend to the idea of the power series. That is, we'll have a series, but it's going to be in powers of x. And then if you think about it, if you substitute values for x, a particular fixed value, then you generate a real series. You generate a series of real numbers like we've been studying. So what's going to happen here is that the power series, what we're going to do here, will represent functions in a new way. And then of course, we'll have to figure out where does this power series make sense? Where is it actually a function? What is the interval on which it actually converges? And so that will be the type of structure that we'll deal with. And all of it's going to come together. And I know sometimes you think, well, it's not going to come together. Yes, it will. The beauty is that all of this fits together. And once you finish the story, you can look back and say, oh, we completed the circle, so to speak. So now just a little bit of bookkeeping. We have a special, so we're going to use all these new constructions. We're going to practice making polynomials, and then we're going to use this idea to look to see how good our approximations are. And I'll show you some really interesting techniques. That's why I want to focus on these techniques to build some confidence. Now, we have a special polynomial. And these are the ones we spend the most time with. We'll practice just with the basic Taylor polynomials, but we have a special polynomial that's near and dear to us. That is, we set c equal to 0. So if that's the case, notice here the c goes away and we end up with a polynomial that looks like this. So we have Pn of f. So we get f of 0. I'll just write out a couple of terms. F prime of 0 x plus f double prime of 0 2 factorial x squared. And then the last term, of course, will be f nth power, or excuse me, nth derivative evaluated at 0 divided by n factorial x to the n. So this polynomial takes up a lot of our time. Of course, the c here, you know, depending on the type of problem you're doing, you may choose a particular c to help out with the algebra. But the neat part about this is that if we do a setup like this, and then we extend to the infinite series, and it turns out that the polynomial or the power series is good for all x, it really wouldn't matter where we actually centered it. So this actually turns out to be so useful that we give it a special name. We call it the Maclaurin polynomial. So we spend a lot of time with Maclaurin polynomials. That is where we take the Taylor polynomial and we substitute the value 0 for c. Of course, you know, the function has to make sense at 0 and all these derivatives have to exist. But if you think about some of your nice functions, it turns out to be good. Now, of course, we have some functions that exist at 0, but then if we go to the left, they're not defined, like square roots and things. So we have to be kind of careful when we pick a C and keep in mind all of our college algebra. We can't just toss that out the window because we're in a calculus class. As you see, when you do calculus, you've got a double job to do. You got to take care of all the fancy ideas of the calculus and then remember all the pre-calc and all of the college algebra, which can be just as difficult. So now let's look at a couple of examples here. Now, think of this just like integration, but we already know how to take derivatives. So let's do some examples where we compute some Taylor polynomials. So the first one's going to be, we're going to say f of x equals tangent x. Okay, and in this particular case, we're going to do Maclaurin. We're going to take c equal to 0. So this will be the Maclaurin. Okay, and we're going to want the third degree or the third order of derivatives. So we're going to do through 3 orders of derivatives. So remember, this will be the third order Maclaurin polynomial. And then of course, we'll talk about some ideas that you know, correlate to functions that we spend quite a bit of time in, like some of the more popular trig functions in e to the x and things like that. So what we can do here is just set up a list. Sometimes I make a table, but since the tangent function doesn't differentiate so beautifully, we'll just do 3 orders of derivatives and then we'll evaluate at 0. So first, let's just do f. Now, when we do a 0 here, ladies and gentlemen, that means no derivative. So f superscript 0 will just stand for f of x. So that means that's the initial function. So that's just tangent x. So here we'll do derivatives. And then over here, we'll do evaluations. All right. So now f1, the first order derivative. So the derivative of tangent is secant squared. Good old Cal 1. And then f double prime. So now we'll use the chain rule. So we'll have 2 secant x to the first power, and then times the derivative of secant, which is secant tangent. So this gives us 2 secant squared tangent. So again, what a lot of you have said, oh, we're doing limits. That reminds me of Calculus 1. This should remind you a lot of Calculus 1. So let's just go ahead and put a box around this and a box around that, so we know exactly which one we're going to use. And then the third, so this is very, very systematic. Lots of times if you don't know what to do with a series, you just look at the Taylor polynomials, the coefficients, and you just start writing, and that gets you somewhere. So this is always kind of like a fail-safe if you forget how things fit together. So like in Cal 1, if you don't know what to do, what do? You either take a limit or take a derivative. So now let's use the chain rule again. So we'll bring the 2 down here with the chain rule for the first factor. So this will be a 4 secant x to the first power, and then multiply by secant tangent, and then of course the tangent that's already there. And then we'll focus on taking the derivative of the second factor. So this will be plus 2 secant squared, and then the derivative of tangent is secant squared. So let's simplify everything. So that'll give us 4 secant squared tangent squared plus 2 secant to the 4th. So let's put a box around this. So again, this is just a use of the chain rule and the power rule. Again, if you like, when you look at this, you can just put a little dot here. That's the first function, and this is the second function. And then, of course, I just drag the 2 along with it instead of factoring it. Then you forget it, and then you get in trouble. All this ink. Let's see, let me get rid of that. Don't need it to be smudged. Now that this doesn't make much an improvement, does it? Okay, now we've got these. So let's go back and see that we just simply need to evaluate these derivatives at 0. And then when we construct the polynomial, put in the factorials and the powers of x. So now we'll say f of 0. So remember, f's superscript. I'm just writing this down because if you ever see this, you won't think it means 1, okay? So now f of 0 is tangent of 0, which is 0. And then f prime of 0 will be secant of 0, quantity squared. Of course, secant of 0 is 1, so that's 1 squared, which is 1. F double prime of 0. Again, we'll just substitute here. We have 2, so we have secant of 0, quantity squared. And then we have tangent of 0. Of course, tangent of 0 is 0, so that just annihilates all of this. So this is just 0. And then the third order derivative, again, we'll go here. We have 4. We have secant of 0, quantity squared, tangent of 0, quantity squared, plus 2 secant of 0 raised to the 4th power. Now, of course, like we had before, and this is not a surprise, the tangent of 0 annihilates the first term, but of course here we just got a secant of 0, which is 1. So this gives us 2 times 1, which is 2. So what we do is we just go up here and notate, put boxes around them to basically tell us that these are all of parts of the coefficients. So now let's go ahead and write down. Now, like I said before, and this is really important, remember the first time you did the law of cosines and the law of sines in pre-cal, you write the formula down, because if you start substituting numbers and you're not organized, you just get a bunch of hash. So what I would say here for some of these, go ahead and write down the formula, then fill it in. So now for the 3rd degree, Maclaurin, and of course, we'll write it in general. Let me just put F here. And of course, we have C equals 0. So this is going to be F of 0 plus F prime of 0 times X plus F double prime of 0 divided by 2 factorial X squared plus F 3rd order derivative of 0 divided by 3 factorial times X cubed. So let's fill this in. So we have P3 of F in this case, where F is tangent X. And so now we see 0 here. So the first term is 0. And then F prime is 1. So this gives us a 1 times an X. F double prime is 0. So we have 0 over 2 factorial X squared. And then F 3rd degree derivative, or 3rd order derivative, is 2. So we have 2. Okay, now 3 factorial, remember, is 6. 3 factorial is just 3 times 2 times 1, which is 6. So we get 6 X cubed. So now if and only if, and we can write it now, we'll just say P3 of tangent X under these hypotheses will now be X plus, in this case, 1/3, 2 over 6, the 2 absorbs, X cubed. Now, you might be thinking, we could just keep going with this, couldn't we? And this is what I was talking about earlier. If you keep continuing with this process and you're thinking, what if we just extended this infinitely? Is that any good? Well, then of course we'd have to do some analysis. So what we're going to find, ladies and gentlemen, is that sometimes the Taylor's theorem is very useful in evaluating the remainder, or at least considering the validity of the particular polynomial and the series if we extend it to infinitely many terms. But other times it might be a little bit cumbersome because keeping track of the derivative. So we may find that we use other techniques to get at the same result. And we're going to find that those alternate techniques coincide with the technique of Taylor's theorem. That is, there's going to be a linchpin that pulls all of this together so that if we have to use another technique to analyze something, are we going to be okay? And I'm going to assure you that we will. So you're thinking, okay, if we extended this, would this pattern start to repeat? And it would, okay? So for tangent, we have this third degree Taylor, or actually Maclaurin polynomial. So let's just say Maclaurin polynomial. So let's just get some practice doing these and then we'll do some error estimates. Okay? The next one I want to do, we're going to change it up a little bit, will be the square root. Now, one thing that you notice, you're thinking, well, if C equals 0, we can get a really nice looking polynomial, you know, in ascending order. And then of course, if C is not equal to 0, we've got all of this stuff. And you're thinking, well, we might have to do a little extra work to make it look like this. So that's what we're going to see in this next problem. So now we're going to have f of x, our friend, the square root function. And we're going to have an order of 2. And we're going to take C, or the center point, or the expansion point, to be, in this case, 4. So we want to compute P2. And in this case, if you consider the notation that we're doing in this case, and it doesn't really matter, we want P2 of F. And this, in this case, will be a Taylor polynomial. Now, when we consider what we're doing in this particular case, and as we write things, I will say this, that we may relax the notation and put X's here, but for now, I want you to know that we're actually basing our polynomial on the function f. So that's a little abuse of the notation, but I want you to get this. So now we're going to do through order 2 derivatives, and we're going to construct just like we did the last time. So let's go ahead and write the first function, that is no derivative, f0 is x to the 1/2. So we're going to compute derivatives. And then we're going to do evaluations. You can make a nice chart, but this is fine. It just spreads things out a little bit. So f prime, our friend from calculus 1, 1/2 x to the negative 1/2. Very simple, power rule. Always good to subtract 1. And then, of course, if we take one more derivative, in this particular case, we'll get 1/2 times a negative 1/2 x to the negative 3/2. So when you look at this particular setup here, we can again move things to other forms and move powers of x downstairs as we need when we evaluate. But I'll do one more level here. This will be negative 1/4 x to the -3/2. Now, if you like and you think that the process of evaluation is easier, you can also do something like this. And this was the next step. We can write like this for ease in evaluation, like this. So these would be, excuse me, more user-friendly forms of our derivatives. No derivative, first derivative, excuse me, and the second derivative. So let's do some evaluations. So now we want f, excuse me, of, in this case, c, which is 4. So this is the square root of 4. That gives us 2. F prime of 4. So now we have this. So we have 1, 2, and then we've got the square root of 4. So in this case, we just get 1 over 2 times 2, which is 1/4. This is very easy stuff, but it's just like doing, you found on the last test, doing integrals and doing series and stuff. There's a lot of arithmetic and you have to be very careful. You have to be very careful. And then f double prime of 4, we'll use our user-friendly form. So this is a -1, 4, and then we have 4 to the 3/2, just like we're doing integrals. And so now this will give us the square root of 4 is 2. So this is 4 times 2 to the 3rd power. And then of course now 2 to the 3rd is 8. So this is -1, 4 times 8, or -1 over 32. So now we can go ahead and box all of these. No zeros in this case. 2, 1/4, and -1 over 32. So now remember, the second degree Taylor polynomial. So there are notations that tend to go between the two. You can just say this is a polynomial in X, or it's a polynomial derived from F. I'll use both. You'll see both of these. That's what I was talking about when I was writing that. So now in this particular case, let's write down what this is going to be. This is going to be f of c plus f prime of c times x minus c plus f double prime of c 2 factorial times x minus 2 quantity squared. So this is what I was telling you before. We get more algebra, we get more stuff here. So we have to be a little bit more careful. So now this implies, we'll just fill everything in. So we have f of c, f of 4, that's a 2. And then for the next one, we have f prime of 4, that's 1/4. And then x minus 2. Well, this is so funny. Let me just go ahead and keep it in general. Just put the c's there and just leave it in general. And then we have what? X minus 2. So here's just the standard formula, and we'll fill in all the details here. So keep those as c's. No reason to go back and forth. And then f double prime. So f double prime of 4 is -1 over 32. Divided by 2 factorial, which is 2, and x minus 2 quantity squared. Now, of course, this is a polynomial, but it's not in the best shape. I mean, if you're doing a physics problem, maybe you're thinking, if I need to evaluate this, that's okay. You know, I can deal with that. But this is not the most user-friendly polynomial. If you're doing an engineering or physics problem, maybe you just want a second degree polynomial, a quadratic that's all combined, so to speak. So let's do a little bit more operating on this to make it, you know, a little bit better to put in our textbook or whatever. So we've got 2 plus, so we've got 1/4 times x plus 1/4 times a negative 2. Now, of course, here we're dividing, so we have a 2 times a 32, so that's a 64. So we have minus 1 over 64. And then, of course, we can expand the binomial. So we get x squared minus 4x plus a 4, expanding that. So now we want to put everything, multiply everything out and collect terms. So we get a 2 plus a 1/4 x. And then, of course, here we get a negative 2 over 4. And again, we may decide that we want to change that up. But for right now, let's just say minus 2 over 4. Maybe we'll reduce that if we need to. We may not want to. So let's just see what we get. So now we've got 1/4 x, negative 2 over 4. And now we have a negative 1 over 64 times x squared. And now we have a positive. So we get plus 4 over 64 times x, negative times a negative. And then we get minus 4 over 64. So when you do these types, excuse me, these types of calculations, it's not always important to look at these things from the standpoint of how we want to deal with these. Now, notice, and you'll see that I've done a real crazy thing here. And I know you noticed this by now, but you all are just so nice. That I've changed my C to 2 here, and that's clearly not what I want. I need a 4. So I'm not really sure why no one said, Professor Ron, that's a 4. So let me fix that. I apologize. Go ahead and take this and let's just switch everything out here. The order is 2, but the C is 4. So don't worry about that. We'll just go ahead and fix it. So let's go ahead and fix this. So this will be P2 of F is 2 plus 1/4 X minus 4. Hallelujah. Good to have the right value of C. This is really why we check what we do. Negative 1 over 32 divided by 2. And then, of course, X minus 4. So again, C equals 4. So again, here, just disregard that. You can just put a line through that. So now let's go ahead and clean this up. So this will give us 2 plus 1/4 times X minus 1/4 times a 4. Again, negative here, 1/4 times a 4, minus 1 over 64. Now we've got x squared minus 8x plus a 16. That looks a little bit better. So again, it's funny how I say it, we have to be careful. And there we go. That's why you write everything down in double and triple and quadruple check. So let's see what we have. So we have 2 plus 1/4 x. And now, of course, we'll just write this as a negative 1. Then we have minus 1 over 64 x squared. And then the 2 negatives, so we get plus 8 over 64 times an x. And then negative here. So minus 16 over 64. So let's collect all of our constant terms and our x terms and our squared terms. So first, we'll just mark everything off. We'll get a 2 minus a 1. So we have this. That's a constant term. And then, of course, we have this term here, which will be, again, 16 will divide into 64 to give us a 4th. So we get minus 1/4. So we've checked that off. Now let's look at all the x terms. So we have 1 over 4x plus, now we can go ahead and reduce this to make the algebra easier. This will just be 1 over 8 since 8 divides the 64 8 times. So 1 over 8x. So this is what I like, just to put checks to say that we've considered them. And then the very last term here is this one, and it's by itself. Right there. So let's go ahead and clean this up. So now, of course, we have a 1 and a 1 minus a 1/4. That gives us a 3/4. And then, of course, we just get a common denominator here of 8. So 2 into 8 is, or 4 into 8 is 2. 2 plus a 1 times an x minus 1 over 64 x squared. So if and only if our second degree Taylor polynomial will be 3/4 plus 2 plus 1, 3/8 x minus 1 over 64 x squared. So like I said, there is not one thing that you do in your work that's unimportant. And so now if you were doing a physics problem and you wanted to make a substitution, you're doing a kinematics problem, and you're thinking, well, this is a much nicer way to deal with the square root. So you use this as an approximation to the square root, as long as you're relatively close to the expansion point 4. And that's what we'll talk about more. Okay, so in a neighborhood of 4, this would make a nice replacement for the square root of x. Again, remember, lots of times as you deal with things, you can just write down what it is, and then to clean it up requires a little extra effort, but not a whole lot. Just make sure that you follow and double check as you move through. Now, let's look at one more. I think it's good practice working with these, and I'm going to do a little estimate with this one. This one's a little bit more complicated, but certainly doable. So for this one, we're going to have f of x equals x squared cosine x. And I'll do an estimate with this one so we move to the next level. And here we're going to take n as the order 2, and our expansion point will be pi. Order 2, so we have second order Taylor polynomial. I just want you to be comfortable with computing these. Sometimes I think you understand things, but your confidence is low. So the best thing you can do is take the notes and just rework all the problems we do and teach them to the wall or teach them to your best friend. So now let's look at some derivatives. And of course, we've got the pi here, so the polynomial is only going to look so beautiful. So we have f0 of x, which is just x squared cosine x. So first degree or first order derivative, we'll use the product rule. So we'll have 2x cosine x. And then, of course, the derivative of cosine is negative sine. So we have minus x squared times sine x. So let's just go ahead and put boxes around these. And then for our second order polynomial or derivative, again, we'll apply the product rule again. So the derivative of x is just 1, so we get 2 cosine x. Now again, the derivative of cosine is negative sine, so we get minus 2x sine x. More stuff, and now the derivative of the x squared is 2x, so we get minus 2x sine x. And then, of course, the derivative of sine is cosine, so this gives us a minus x squared cosine x. Now, when we look at this, we're going to get some additional copies in this particular calculation. So what's interesting about what we do is, as we look at the derivatives, we're thinking we can just go ahead and combine these two, and these, of course, are different. So this will give us 2 cosine x minus 4x sine x minus x squared cosine x. So let's go ahead and box this. I want to spread this out a little bit more so you can see all the computation here. So now we want to do some evaluations. So evaluations. So f of pi, again, our expansion point. So this will be pi squared times cosine of pi. And this is going to be interesting when we do an approximation. So this will come back to haunt us. And of course, this will be pi squared. Cosine of pi is -1. So we just get negative pi squared. And now let's do the first derivative, f prime evaluated at the expansion point c. So we're going to get a 2 pi times cosine of pi minus pi squared times sine of pi. Of course, the sine of pi is 0, so that term is annihilated. So we get -1 times 2 pi, which is -2 pi. So let's go ahead and box these. Constant f prime of pi, and then of course, f double prime of pi. We'll get 2 times cosine of pi minus 4 pi sine of pi. And then I'll put this here, minus pi squared cosine of pi. So of course we have 2 times a -1, so that's a -2. And then of course we have a minus pi squared times a -1. So this gives us pi squared minus 2, if we just write the positive term first. So again, this is very, very rudimentary, but again, new. So it's always good to write down what it is you need. So in this case, let's just write down the formula again, and I'll be sure to use the correct C this time. So the second order Taylor polynomial for f, or also written P2x, is going to be f of c plus f prime of c x minus c plus f double prime of c divided by 2 factorial x minus c squared. Just remember, as you raise the order of the derivative, you have the concomitant factor of n factorial in the denominator. That's always easy to forget. So that's why I write these down to remind you. You just be working along, you throw in the derivative, and you forget the factorial. That's easy to forget. So just be mindful of that. So now what do we get? So P2, in this case, I'll just go ahead and put it in, of x squared cosine x. We'll just go ahead and fill all of this in. So we have f of pi right here, negative pi squared. And then for the f prime of pi, f prime of c, we have minus 2 pi. And so this will be x minus c, of course, x minus pi. And then the last one, we have what? We have plus pi squared minus 2, of course, and then 2 factorial is 2, times x minus pi quantity squared. Now, when you look at this, this is like we had before. This is constructed. It's a Taylor polynomial, degree 2, expansion point, center point, pi. Everything's good, but it's not in the best form. So let's go ahead and clean it up. Again, this is fine if you're going to evaluate it at pi. X, put in pi here and you're good to go. So that's why many times we just say P2 of x to evaluate. So I write it this way to kind of inform you that it's based upon this function. And then of course we often use this notation. So I will probably toggle between both. So now let's go ahead and clean this up. So we have negative pi squared, and then we get a negative 2 pi times x. And then of course we have a negative negative. So this is a plus 2 pi squared. Now here, of course, we go ahead and divide if you like. This will be plus, so because of the exact nature of things, that's going to give us more work to do. So we have pi squared over 2. And then, of course, negative 2 over 2, that just gives us a minus 1, if you will, just to make that a little simpler. And then we can expand the binomial, x squared minus 2 pi x plus pi squared. Again, very boring. I'm sorry, this is kind of boring right now, but it will pay off handsomely. This type of arithmetic is just like doing series convergence test. Not much glamour there. Not like doing an integral, which makes you feel great. Just somewhat rudimentary. So now let's go ahead and multiply things out. So first, I'm going to notice that we can just go ahead and combine this and get a pi squared. Just go ahead and put that out of its misery. And then we have a minus 2 pi x. And now we want to hit all these with a pi squared over 2. So we get plus pi squared over 2 times x squared. And now, of course, here we're going to get a pi cubed, but the 2's will absorb. So we get minus pi cubed x. So notice here, the 2's absorb, negative 3 copies of pi and an x. And then lastly, we'll get 4 copies of pi divided by 2. So again, very, very simple, not difficult, but important that we write things correctly. So again, notice here, pi squared over 2 times pi squared is pi squared over 4. So that's taken care of. Now let's hit everything with the negative 1. So let me make sure that looks like a 2 there. So we've got minus x squared, then minus minus, plus 2 pi x, and then minus pi squared. So when you look at all of this and you think about what we're doing, we're at the same point we were last time. So let's go ahead and combine everything. So let's look at all of the constants, pi squared. Let's move down here, no more constant. Well, there's 1 plus pi squared over 4, or excuse me, pi to the 4th over 2. Check. And then down here, a minus pi squared. Well, those are going to absorb, so that's good. Now let's look at all the x's. So we've got a minus 2 pi x. Just check them off. And then we've got a minus pi cubed x. Check it off. And then we've got a plus, well, that's going to absorb too. Well, how interesting. So we've got 2 pi x. Check. And then lastly, let's look at all the x squared terms. So here's one here. Pi squared over 2 x squared. Check that off. And then as we move down, and of course I did that one right here, so I didn't check that one off. And then of course a minus x squared. Check. So now what we can do is combine the like powers, the like terms, and the rest we just write exactly. So what does this give us? This gives us pi to the 4th divided by 2. Now, of course, these absorb, and we get minus pi cubed x. And then, of course, here, the best we can do is just factor the x squared. So we'll get plus pi squared over 2 minus 1 times an x squared. And here is our second degree Taylor polynomial. I'll put the x in now that we can relax a little bit. So when you look at this, we keep everything nice and exact. And this is, again, it may be more fortunate with your calculations to use this approximation than this function. And again, when you think about what your calculators do, they love polynomials. because you can multiply, divide, add, subtract kind of thing. And this is what your calculator likes. So you don't have little cosine men that live in your calculator. You have infinite series that live in your calculator in the coding, which can be easily manipulated. So the key here is that, again, there's nothing wrong with what we get right out of the box, but it's not very user friendly. This is a lot better when we're trying to do calculations with other disciplines. And this is much more user friendly in ascending form as we normally think of a polynomial. Like in college algebra, oh, do I have to write it in ascending form? I'm like, please go ahead. Unless I ask you to completely factor it, I want a nice ascending form polynomial. College algebra students don't always like to have to do that. So now let's just go ahead and see, let's think about error here and just think about how good things are. So here's what I want to do. So we want to use this polynomial. I'm just going to move this up right here so we can still see it. We want to use this polynomial in an exercise. So for instance, if we look at this, notice we have this expansion point C, which is pi. And what we want to do is let x equal 7 pi over 8. So this is to the left here. So we'll say, you know, something right here. I didn't, of course, I'm making up my own scale here. So I've got this little interval here. And what we want to do is just go ahead, and we'll use Google to do this. Go ahead and compute the value at 7 pi over 8 with our polynomial here, and then compare it using Google with the actual function and just see, okay, what relatively, how do they look, you know, when we make a comparison. So we want to compute, and this is why I'm relaxing to this notation. And this is, again, the last problem, f of x was x squared cosine x. So compute P2 of 7 pi over 8, compare to f of 7 pi over 8, okay? So that's why I wrote this way. And then, of course, you could think, well, we could leave it in the other form and do that, no big deal. But it's good practice, because when you look at Taylor polynomials, they're always written this way, and you need to be able to do that computation. It's not hard, but it's something you have to practice. So now we'll say P2 of 7 pi over 8, and we'll use our formula here. So we get 4th power of pi divided by 2 minus 3rd power 7 pi over 8. Then we have plus pi squared over 2 minus 1. And then we have 7 pi over 8 quantity squared. So a lot of beautiful numbers here. So we've got this. So again, this is the formula we're using. We're just substituting the value 7 pi over 8 for x here. So let's clean this up a little bit. So we get pi over 4, or excuse me, pi over 4. That's like saying trigonometry. The 4th power of pi divided by 2, let's put the 4 where it belongs, minus, and then of course here we'll have 7 pi to the 4th power over 8. And then of course we'll multiply here. So let's go ahead and write this out. Pi squared over 2 minus 1, and this will give us a 49 pi squared over 64, if we just simplify that with the laws of exponents. So now, if you will, we'll get a common denominator here of 8. So that'll be a 4. So we have a 4 pi to the 4th minus 7 pi to the 4th. So that takes care of these two guys. Then we have plus, let's go ahead and multiply. So this will be a 49, again, pi to the 4th. And now we have a 2 times a 64, so that's a 128. And then minus 49 pi squared over 64. So lo and behold, we get a bunch of beautiful numbers. Now, of course, these, when we look at all of this, this is kind of out by its lonesome, but this is the same type as this, so we can add these. And now notice, just do a little factor tree. We can do 4 and 32, and then 4 and 8. So this will just be what, 8 times 16. So we can easily get a common denominator here. So we'll do 128. Of course, that's just, that's a -3 when we do the subtraction. So 16 times a -3, that's a -48 pi to the 4th. And then we have plus the 49 pi to the 4th. And if you will, 2, so that'll be minus 98 pi squared. So this gives us pi to the 4th minus 98 pi squared divided by 128. So of course, if I were on a test, I could say, find the exact value of P2 at this number. And it would be that. Now, this is where we can use Google and we can get a nice approximation to this, but let's hold off on this. Now, the next, so there's our P2, and then F of 7 pi over 8. That'll just be, again, 7 pi over 8 quantity squared. Of course, this is in radian measure, 7 pi over 8. And of course, that's not on the unit circle, so we'll leave it as it is. So this gives us 49 pi squared over 64 times the cosine of 7 pi over 8. So these are the exact values. Now, this is where I just used a Google approximation in the radian mode. So let me just go ahead and pull that up. I've got Google here shared. Let's see. Yeah, there, well, ding. Just a second. Let me go here and move it around a little bit. Sometimes I have to move the Google to get it to find it. Okay, so share screen. There is Google. Okay. So here we go. So now for the first one, we'll have parentheses. So we'll get, we'll use the pi and then the exponent key to the 4th minus 98 times pi squared. So this is where the Google calculator is a big plus. Gives you a nice calculus approximation divided by 128. Clear that out. 128. And this gives us, we'll just write out several decimals, approximately -6.795407. And there's another 0. 7954073. So -6.7954073. And now let's do the exact value. So we'll have, in this case, 49. I don't need parentheses here, but I'll go ahead and put them in. 49 times pi squared divided by 64 times, again, we're in radian mode, cosine of 7 pi over 8. And I won't use it. I don't need extra here. So 7 times pi divided by 8. Now I know you all know how to use these things, but I want you to be able to use the Google. So this will be approximately -6.98121796. So what I was what I want to show you at this point is that what we're doing is not just a bunch of hash. These are, at least for a second degree approximation, this is not half bad. Now, the key here is that it's like, well, we've got calculators. Why would we ever need this? The computations may be made more simple. That is, if you're working in close proximity to pi, this may be much more usable, okay, in terms of your calculations. And it's like using x to approximate sine x when x is close to 0. It's a lot simpler to use. Transcendental functions are complicated. This isn't, okay? Polynomials are super, super simple when it comes to computation. Now, finding zeros, that's completely different. That's a hard job. But working with them arithmetically, can't beat it. So now this is kind of the idea I was talking about. If we use the polynomial here as a replacement, in this case, for this, as a replacement. So let's go ahead and look at some more details. So again, maybe opening the story a little bit more. Now, with this in mind, now hopefully you feel that what we're doing is not just simply off the cuff. Let's study this a little bit more. Now, in basically trying to become comfortable with this, we can just write down a function and then give a particular approximating polynomial. So here's an example where we have f of x, our friend, the inverse cosine. Okay, and now what we're going to do is we're going to take the Maclaurin, c is 0, and we're going to take the expansion point in this case. Again, the expansion point is 0, and we're going to take the value of x in this case to be 3/20. And let's just see here. Let me see how I want to set this up. Yes, so, okay, right. So we want to, I'll write this down this way. We want to approximate f of 3/20, and I'm going to write it down using the first order Maclaurin polynomial. I'm phrasing it a little bit different than you might see it. Maclaurin polynomial. So I want us to just to go ahead and figure out what it is, okay? So we want to approximate this, just like we did before we used P2, we're going to use P1 in this case, and then we're going to use Taylor's theorem to get an upper bound on the error and not think of the Google calculator like we did last time. So we're going to move to the next level. So here, F0 is just the function. Now remember, with Taylor's theorem, we have to bump up to the next order of derivatives. So to evaluate the remainder, we're going to need the second order derivative. So now the first derivative, we know from the first week of class, this is just -1 over the square root of 1 minus x squared. So let's write it in a user-friendly way. Our friend from the very first week of Calculus 2. Okay? And then f double prime that we're going to need for the remainder, we can just apply the chain rule. So we bring the power down, that'll be a positive 1/2, 2 negatives, 1 minus x squared to the -3/2 times the derivative of the inner function, which is -2x. So again, the 2's absorb. So this gives us a -x. Then downstairs we have 1 minus x squared to the 3/2. Okay, so the interesting thing here that we have is we added one more tier to the analysis. This part will deal with the remainder, and I'll just go ahead and start using the x's now, even though I like to use the f's, we'll use the x's. The remainder for the first degree polynomial requires the second order. So we step up one more level of derivative. So now let's just go ahead and evaluate. The problem was given where they just basically gave you the polynomial, but I don't want to do that. You're not experienced enough for that. So let's go ahead and figure it out. So now f of 0. So in this case, we get what? Inverse cosine of 0. Again, just the unit circle. We know inverse cosine lives between what? 0 and pi. So that's pi over 2, right? So that's just the unit circle. So again, cosine of pi over 2 is 0, so that we flip it around to get the value. I know you all know this, but I'm acting like you're in pre-calculus. And then f prime of 0, again, we'll just substitute. So this will be negative. So we get 1 minus 0 squared to the negative 1/2. So this will just be a negative 1. So the idea here is that when you look at this, you're thinking, okay, this is what we did before, but so much less work, and we like that. So this implies that P, let's just write down what P1 of X is. Well, we want not do implication yet. Let's just write down what it is. This is just going to be F of C plus F prime of C times X. And of course, remember, C is 0, but let's just not even assume that we know that yet. And so now we'll fill everything in. I'll just write this in. So now we're going to take C equals 0. So this implies P1 of X. So we have F of 0, which is pi of 2, pi over 2, and then we have the minus. So we've got X here, and then we have the derivative, which is negative 1, so we get minus X. That's it. That's how simple it is, right there. Okay? So we don't even have to really figure out what P of 3 over 20 is. We just want to get an upper bound on the error. So approximate using, and I'll just say, get an upper bound on error, because that's the best we can do. So now what we're going to do is just analyze this. So remember, R1, let's write down what it is. The remainder will be F double prime at some Z, again, between, so we're thinking this way, we've got 0 and we've got 3 over 20, and Z lives somewhere in between, divided by 2 factorial, in this case, and then we just have an X squared. So that's basically what the remainder is going to be, and we're going to look at its absolute value. So what we want to do to make this cogent is to just maximize the derivative. In a lot of these cases, when we can't really maximize the order of the derivative in the remainder, we go to other avenues. So this is where we get an upper bound, just an upper bound, and don't worry about doing anything any fancier than that. So basically, get upper bound on, in this case, F double prime of Z. And let's write that down. So in this case, we'll just maximize this for X. So this implies, So we get to use this guy here. So we'll say absolute value, R1, and our X in this case will be 3/20. And this will, and we're going to say in this particular case, let me do it this way. Let me just go ahead and write it this way. We'll do the remainder part last. I'll just say F of this double prime, and we'll do the max. Let's do this first, right here. And so in this case, we have X between, or we'll just say 0 to 3/20. Since I'm going to write that, let's go ahead and put the X here for now. So we'll say, okay, well, this upper bound, let's just see, what does this look like? So it's right here. So now when we look at this and we take X, in this particular case, we're seeing that on this interval, this will be largest when we make the denominator the smallest. So we evaluate at 0, and then of course we want to make the numerator as large as we can. So we evaluate at -3/20. So this will say, using this, 3/20 negative, and then downstairs we want to make that as big as we can. So we make the fraction as big as we can. We make the denominator as small as we can. So that'll just be evaluation at 0. So this is kind of like common sense upper bounds. And and of course, make it, sorry, I'll get it. So think about what I just said here. If I make this smaller, if I put it at 0, that's as big as it can be. So take the opposite of what I did. If I make it as small as it can be, I'm going to evaluate it 3/20. So that makes a little bit more sense. So let me write that in. So this is going to be 1 minus 3/20 squared to the 3/2. Let me give it a little bit more space here. Squared to the 3/2. And so now what does this give us? Well, we'll do absolute values. So we'll get 3/20. And then downstairs, we'll have 1 minus 9/400 to the 3/2. This is, again, just think about fractions. Make this fraction as big as possible in absolute value. You want to make the numerator as large as we can in absolute value, and the denominator is small. So that's why we do this. So of course, it's all self-correcting as you use a very basic common sense approach. And then now we get a common denominator, so we get 3/20. So here we've got what, 400. So this will just be 400 minus 9 to the 3/2. So this will give us 3/20, and then I'll invert this, but that'll just be 391 over 400 to the 3/2. And then you can invert it, just bring it upstairs. So this will be 3/20, 391, 400 to the -3/2. So this is an upper bound on the second derivative absolute value. This is how we use Taylor's theorem. That way we don't know what Z is, ladies and gentlemen. We don't know what Z is. We know it exists. And this is why we say, okay, what's the best thing we can do? And what we're going to do is we're going to get an error upper bound that's actually worse than it is. The actual situation is better. But again, we can't get our hands on Z. Theoretically, it exists, but it's very hard to determine what Z is. So what we do is say, okay, instead of hypothesizing about what Z is, let's just see how big this derivative can be because it's evaluated at Z. How big can it be on the interval that we're considering, 0 to 320? Because remember, Z is between X and C. or in this case, there's C and there's X. C is between those two. So now what does this give us? Next sheet of paper. So with this particular construct, what we're seeing is that we can now go back to the remainder, which is up here. So let me write this down. So let's get an upper bound on the remainder. So R1 of X in absolute value equals, again, F double prime of Z divided by 2 factorial X squared. That's what it is. And so now we want to let X equal 3/20 and use upper bound for absolute value of F double prime X that we just have right here. Okay, so we have R1 320 in absolute value, and we'll just go ahead and write it in. So this is going to be less than or equal to, okay, we've got the 1/2 and we've got the X squared. So we have 1/2 3/20 squared. And then we have, in this case, this dude right here. So I won't even write it down. I'll just go ahead and put it in. We know what it is. So basically, we take the absolute value here, we get the 1/2, we get the X squared, and then we have our upper bound right here for this guy. So let's write it in. 3/20, 391, 400 to the -3/2. And so when we look at that, we're like, oh, eureka, how fun. So now let's put all the powers of 3/20 together. So this gives us 1/2 3/20 cubed 391 400. This is what I wanted to spend more time on, because this is not a simple construct. It's easy to do piece by piece, but again, let me reiterate, we can't get our hands on Z. We know where it lives, so we just want an upper bound for the derivative using a more common sense approach. How do you maximize a fraction? Make the numerator as large as you can, make the denominator as small as you can, if indeed you can do that for that particular interval, which we did right here to get this number. And then when we want to find the actual upper bound for the remainder, in this case, for this value of X, we can simply fill in this upper bound and then the other parts that come from Taylor's theorem. Now, we just say this, upper bound for error. Now, again, ladies and gentlemen, the upper bound that we construct here is actually worse than the actual case. The actual case is a little bit better, but all we can really do is get an approximation of it, and we're happy with it. So if we can make this good, then we're in good shape. Now, of course, if you go to Google, let's go to Google and get an approximation of this. So let's stop the share and go back to Google. So let's clear this out. So let's do this. So we're going to have 1/2 times, then we'll do 3/20, 3 divided by 20, just to kind of get a ballpark figure of what this is. And we'll do our power, we'll do 3. So we got 3 copies of that, 3. And then times, the last bit will be 391 divided by 400. And this will be to the -3/2. So we'll do our power, and then we'll do parenthesis, -3 divided by 2. So it's nice that we have the power series in our calculator. And this gives us 0.001746. So we can at least see here that this is not shabby at all. And this is actually worse than it actually is. If we use, in this particular case, if we use the first degree Taylor polynomial to approximate f of 3/20, we're getting a fairly small error, and this is actually worse than it actually is. So we're thinking, wow, we'll take it. So with the first degree polynomial, which is just this simple guy right here, Maclaurin pi over 2 minus x, we're thinking if that's all we need for our calculations, we can see this is complicated. This is easy. In physics, physicists love Taylor polynomials. They love Maclaurin polynomials. They make their computations simple because you do local computations, okay? So the idea is that since we can't get our handle on Z, and I do this very precisely, and like I say, ladies and gentlemen, as a working mathematician, we always have to kind of navigate the waters by saying, what is it we exactly want to do here? And that's what's bringing you to the next level. That's why the Calculus 2 course really does tax you in a very mental way, using all of the stuff that's come before you. So we can get an upper bound on the second derivative and then get this. Now, that's an excellent problem, but I think I took it to the next level to make it more interesting. Now, here, let's do one where we do the sine function. Let's see, let me find one that's kind of interesting here. There's so many interesting problems to do, and I like all of them. Let's do a sine function. Now, there are some really nice Maclaurin polynomials, sine, cosine, and e to the x that are real simple. But here's an example that says, okay, it says determine, let's see here, yeah, determine, so we're doing the same thing with the error, but phrasing the problem a little bit different. Determine the degree of the Maclaurin polynomial to achieve error less than 1/1000. And here are the hypotheses. We have f of x equals sine x, and we want to approximate in this case, f of 3/10 with the given error here, with error less than 1/1000. Now, we love sine functions because when we differentiate sine, we get sines and cosines back. And that's easy to analyze. So in this case, what we've got our 0 here, we've got our 3/10 here, and then of course Z is going to live somewhere in between. Okay, so this type of argument should start to sound familiar. So we're thinking, okay, we need to analyze the remainder and then work backwards. Now, I'll show you in general what the polynomial is going to look like. It's very simple. So we have a nice trick here. For sine x, f of x equals sine x, we'll say the maximum of, in this particular case, say x lives between 0 and 3/10 for the n plus first derivative. So this is more in general now, okay? Because last time we were just focused on the second degree because we started with the first. Now we're not starting with anything. We're just going to figure out which degree we need to make the error less than 1/1000. So basically, we get sines and cosines. What's the maximum of the sine and the cosine? 1. So we just say 1. So this is a simple upper bound that's independent of n. Simple upper bound, independent of n. I mean, sometimes we have to do a lot more work. You saw what we had to do with the inverse cosine. This is nice. A very simple upper bound for any sine or cosine function, plus or minus, will always be 1. So we can hang on that and know that we will get at least a decent upper bound for the remainder, which will be the error in our approximation. So now this implies that in this particular case, we'll have the absolute value of the remainder, and of course we're using 3/10. And let's just go ahead and fill all of this in. So we have f n plus 1 will be evaluated at z. Remember, z is between what? C and x. Then we have n plus 1 factorial. And then, of course, we have x is 3/10 to the n plus 1. Okay? So, like I said before, the key to Taylor's theorem is using it. The proof is beautiful, but it doesn't help you use it. So that's when I have to kind of weigh which is more important. So now if we look at this, we just replace the absolute value of the nth derivative here with 1. So this gives us a simple upper bound. So we get what? In this particular case, 3/10 n plus 1 divided by n plus 1 factorial. Or you can write it as multiplied if you want. So this is where you're thinking, oh, isn't that interesting, Professor Ron? How do I work with this? Well, this is where we test values, because notice we have a factorial here and we've got an exponential here. And so we don't really have a simple way to solve for things. So we can just test values of n and see which one, the first one gives us what we need. So remember, we need this to be less than 1/1000. You think about the problem on the last test, we used the improper integral, and just it was a very simple improper integral, so it was easy to figure out what n was. I mean, it fell out of the woodwork. That was really easy. This is a little bit more complicated. So what we want to do is test this. So we'll say check values of n. Check values of n. So let's look at it. Let's just start with 1. I mean, you know, we don't really know. We're just looking here. And this will give us a little bit more practice. So when we have 1, let's look at what this is. This will be what? 1/2 factorial, 3/10 squared. Okay. So this will be 1/2 times 9/100. So this is 9/200. And this is way too big. This is certainly a lot bigger than 1/1000, so that one doesn't work. Let's try n equals 2. So now n equals 2, we'll have what? 1/3 factorial, 3/10. Okay, 2 plus 1 is 3. So this gives us 1/6. And so now we're going to have what? 27, 3 cubed. These are easy numbers over what? 10 cubed, 1,000. So now if we divide by 3, here we get a 9 over a 2, 1/1000. Now, if we look at that, that's 4 1/2 times 1/1000. That's clearly bigger than 1,000. So this is too big. So not clear. So let's try n equals 3. So now we have 1, again, n equals 3, we'll have 4 factorial, and then we'll have 3/10 to the 4th. So 1 factorial, or 4 factorial, is 6 times 4, which is what? 24. So we have 1/24. And then we have 3 to the 4th, that's 81. And then, of course, 10 to the 4th, that's 10,000. So now let's just go ahead and reduce this and see what we get. We can divide by 3. So that's going to be a 27. And then, of course, here we get an 8. And if you like, we can go ahead and take out one of the 10s here in the denominator. So 1/10, 1/1000, just as a little bit of general math. That's all I've been doing today is general math and algebra 1, if you think about it. You know, how do you make fractions maximal? I mean, adding fractions, general math and algebra 1. And now notice here, this is going to equal 27/80 times 1/1000. Well, of course, this is a number less than 1, so this is clearly less than 1/1000. So this will work. So now this just says select n equals 3. And so we will have the third degree polynomial. And if you do it for sine, it's easy. You just get x minus x cubed over 3 factorial. These are easy. These polynomials are easy. And that will do it. So this is just x minus x cubed over 6. So physicists love this. So now what you're seeing, remember, sine x over x goes to 1 as x approaches 0. So when x is really even closer to 0, sine is approximated by x very nicely. So this goes back to the point that the limit as x approaches 0 of sine x over x equals 1. Basically, x over x is 1 when you're close to 0. So that, again, is consistent with what you did in Calculus 1. So all of this fits together, ladies and gentlemen. This kind of helps us to complete the circle. Now, there's another example here that I want to go over to finish. So when you're doing these kinds of problems, basically use this as a recipe to analyze the remainder using your C and your X, okay? And then remember, you've got to get a simple upper bound for the derivative, the n plus first derivative. And usually with the fraction, you can use the technique I used, make the numerator large, the denominator small. That maximizes the fraction. And if you've got trig functions like sine and cosine, you can always use 1. Very, very nice. And of course, you know, this is maybe not as good as it is. This is, we see here that we get an upper bound on the error. So it could be actually even better. So we're making the problem even better by choosing our analysis to go with the upper bound. So we're actually making the problem better for us. Now, so they're just for instance, when you think of let me just give you a couple of polynomials here. Say we did the, let's say we did the 5th degree for sine. It looks like this, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So this is a nice odd function as sine needs to be, and this is for f of x equals sine x. Let's just write down the 5th for cosine too. It's going to be an even function. It looks like this, x1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. But the 5th degree term is 0, so that's the best we can do for that. Notice the odd ones just 0 out. And these are Maclaurin. That is C equals 0. This is f of x equal cosine. So you can easily verify these. I didn't do these. These are so easy. You can do these in your sleep. I did much more complicated ones to get you used to the arithmetic. And then we can do a 5th degree for e to the x. It looks like this, 1 minus, plus x squared over 2 factorial plus x3 over 3 factorial plus x4 over 4 factorial plus x5 over 5 factorial. And this is where f of x equals e to the x. So the thing is that all of these are going to be extended infinitely to infinite series. And we'll be able to analyze the remainder to verify them. But the e to the x Maclaurin, all of these are Maclaurin, C equals 0. See how easy these are? These are so easy to remember. x to the n divided by n factorial. Here we just have even powers of x, cosine is even. Here we have odd powers of x, sine of x is odd. So this is all in concert with what you already know, as it has to be, as it has to be. This is how your calculator works, ladies and gentlemen. This is how your calculator works. So now you're actually getting to the point to why I don't allow you to use calculators except at the very end of the problem where we just look for an estimate, because this is how the calculator works. That's how it works. So let's do one more example just to get it set up. So this is another possibility that we can do. This is a nice example. It says determine, and I know I have this written up in the Blackboard notes, determine values of x for which, this is a famous problem, for which the function, and I'm going to use the e to the x this time, for which the function can be replaced. So I'm rephrasing these problems so you get more use of them. Can be replaced by the Taylor polynomial, by the, in this case, it's going to be Maclaurin. I'll go ahead and write it as Maclaurin. They're all Taylor polynomials, but the Maclaurin are the ones when c is 0. If error is less than 1/1000. So we're going to have, in this case, f of x equals e to the x. And we're going to have the third degree polynomial. You know what it looks like. Just chop off the last two terms that I wrote with the last one. We get 1 plus x squared over 2 factorial plus x to the fourth over, x to the third over 3 factorial. Okay, so now what we, and here's the key, here's the caveat. X is less than 0, so you can get an upper bound. So in this particular case, what we want to do is say, okay, if that's the case, that's going to make the upper bound really easy. So we're interested in this case, now we don't know what x is now. I can't put in like 3/10 or 3/20 because I don't know what x is. We don't know what x is. We have to figure out what x is. So here, let's just write down what the remainder for the third degree polynomial is going to be. And this is going to be what? The fourth, n plus 1, evaluated at z, divided by 4 factorial times x to the fourth. This is, you're going to love this problem because it's easy compared to the last ones. The ones with all the numbers are much trickier. So I kind of saved this for last. Now, here's the deal. When we take derivatives of e to the x, we just get e to the x. So we observe that the fourth derivative of e to the x is e to the x. And so this implies that the maximum for the absolute value of this derivative, in this particular case, when x is less than 0, will just be the maximum x less than 0 for e to the x. But this is an increasing function, so this is just going to be e to the 0, which is 1. Because again, the function's increasing, and if x is less than 0, 1, which is the y-intercept, is the maximum. So that's why this is a nice little caveat here. It makes the problem like a sine function, like a cosine function. So we're like, yay, hallelujah, we didn't have to work so hard. So now we can go up here and say, okay, let's get an upper bound on this. So this equals, what do we have? We've got what? E to the z divided by 24, x to the fourth. So when we take the absolute value here, we get the absolute value of x to the fourth. We get e to the z, which is positive, and we get 1/24, which is 4 factorial reciprocated. So now we use our upper bound here, which is 1. So this is less than or equal to x to the fourth over 24. Again, we replace the maximum of e to the z with 1. We're thinking, yay, how simple. And then we want this to be less than 1/1000. So this problem actually evolves a little more quickly because we have less numbers to worry about. In the previous problems, we had all these numbers running around. So here we're actually saying, okay, if I'm going to start with this, think about the last problem, we figured the order of the polynomial. Here, we're starting with this polynomial, and we need to figure out which values of x will work well if we want error to be less than what? 1/1000. So now this is easily solved. So if and only if x to the fourth in absolute value is less than 24. So if you will, let's just write this as 12. Let's see, what would be the best way to do this? Let me do it this way. We've got an 8 here. We don't have a 12. I know we've got an 8. So 24 is 8 times 3, right? And then 1,000, let's see, what's that? So we'll get a 1, and then we get a 2, and then a 4, 40, yeah, there we go. That'll work, good old general math. So the 8's absorb, and we get 3/125. So now equivalently, this is just a conjunction. So this means that x in absolute value will be less than the fourth root of this value. And then, of course, this spreads over either side. So now, if and only if, we have negative 3/125 to the 1/4 less than x less than 3/125 to the 1/4. But now this part we omit because x is less than 0, so we omit this. And so this implies that x will just be in this interval right here between what? The negative 3/125 to the 4th power, 1/4 power, 0. So what we're seeing here is that the x's that will work when we're less than 0, for this to give error less than 1/1000, they must live here. And then if you do, you can use your Google to get a nice approximation of this, but this is exact. So what we're seeing is that sometimes we don't have to work very hard. We sometimes you're thinking if we're trying to find an upper bound for a derivative, we have to find a formula for it, like we did, in Cal 1. If we've got like a rational function that has a factorial in it, we may have to do a little bit of detective work to figure that out. But in this case, since x is less than 0, we get a real simple upper bound. And so even though this is maybe not the true story, we know it will work for this. It could be even better than this, and it probably is. But we know it is because we took an upper bound here. So the idea is that for these values of x, this will give us an error of less than 1/1000. So in summary, what we're seeing is that the Taylor polynomial, or the Maclaurin polynomial as we have here, is basically a substitute for the function. And that means that we have derivatives. We've got continuous derivatives. We got to have a nice, well-behaved function, but then we can replace the function with a polynomial, which is easy. Ladies and gentlemen, polynomials are simple. We can manipulate them. We can differentiate them. We can integrate them. We can add, subtract, multiply, divide like you wouldn't believe. Transcendental functions are difficult. Your calculator doesn't look at them like we think of them in the abstract. The calculator thinks of them this way. And this is the beginning of what we call modern analysis, where we replace the function with a polynomial. So I hope I've gotten you at least entrenched in the idea that the Taylor's theorem basically is a treatise on how good is the approximation. Look at the remainder. When we can, this analysis is fine. However, this analysis may be exceedingly difficult for certain functions. And so we'll have to try another approach to get at the answer. So when it's available to us, this is fine. But when it's not, we have to think, is there another way to do this so we don't, go crazy kind of thing? So What I wanted to do today is emphasize the arithmetic of Taylor's theorem and emphasize the fact that every step is important. It's kind of like, let me just, in closing, let me just share one thing with you. Where is this? Oh, let me pull this up. Let me get, there we go. Here are the solutions to the last test. Ladies and gentlemen, this was an easy test in the sense that all I did was test you on things I taught. And a lot of you, you know, my hat's off to Lucinda. Lucinda, you did a great job with the partial fraction decomposition. That was great. A lot of you did, but I needed to see this. And I was very impressed with a lot of the work. I want you to go through this and just make sure that you have the basics down. I gave you a real simple telescoping theorem. I mean, it was like obvious that it telescopes. You didn't even have to do extra work or decomposition. On Taylor's theorem, or excuse me, on the integral test, I wanted to see the actual hypotheses. Very few of you did that. I'm not really sure why. This was using the integral test. I was fairly pleased with the trig sub. I just made up these limits to work, so you get really nice limits here. Most of you did very well with that. This problem was like the first week with partial fraction decomposition, where you have to rig the integral and then you get a simple inverse tangent. Fairly good on that, but in some cases, a lot of you punted on this, and I wasn't too happy with that. The limits, you all did the same thing I did. You just used e to the ln, and it accomplished the same thing. So I thought that was kind of a neat way to do it. And then, of course, the Weierstrass, some of you just got confused with the cosine. You put sine in here because I switched this up from the notes. That was a sine, and I switched it to a cosine just to make it interesting. But that was a very straightforward calculation. And if you do it the way I taught you, it's much easier. Some of you want to go a more convoluted approach, and that's okay. I'm all right with that. It's just that it's not always necessary. So go through these solutions, make sure you've mastered the techniques, spend time on the Taylor's theorem. That is, make sure that you go back through these items that I've talked about today and get them up here. This is essential material, and it will play a role in power series. It will play a role in the manipulation of power series for the rest of the chapter. And then, of course, after this, we'll head into polar coordinates and parametric equations and all that fun stuff. So you'll feel like you're in physics again. But just remember, I've tried to focus on the arithmetic and the algebra of the Taylor polynomial. So spend some time with this and really get it in your brain, because this is the essential part of how your calculator works. And you future engineers will be using this, you future financiers will be using this, future medical doctors, maybe not so much, but it will certainly be a reason as to why you can pick up the technology and it works. So thank you for staying a little later today. I know I've been very long-winded, but I can easily tell how much time things are going to take. These are not easy concepts, ladies and gentlemen. That's why you need a professor like myself to be able to explain them, because I'm going to work out everything in complete detail. And that's what I want you to master, because I want you to get better at this. I want you to raise your level so that you can reason correctly. That's the whole reason why I teach and why I love to do mathematics. It's making math available to STEM majors so that they can be the best they can be. So you all have a great day. And if I see you at the conference hours, wonderful. If not, I'll look forward to your WebAssign messages in our next class. Have a great day, everybody.